Okay, very good. So like we uh, promised last time, we're going to complete chapter 3 today. It seems like we're going slow, chapter 3, just chapter 3. But speed doesn't matter really. So we will do Green's reciprocity relation, we will do multipole expansion, and if time permits, I want to do some discussion of the magnetostatics ideas. Okay, so we'll take a look at that. And for the last time, we saw the Green's reciprocity relation, which just tells you if you have two different charge distributions, then you can write down the total electrostatic energy of that charge distribution in two different ways. First one is thinking of the second charge distribution as sitting inside the first charge distribution, or you can think of this as the first charge distribution sitting inside the potential created by the second charge distribution, right? So that those two things are equivalent, and it turns out to be useful in solving quite a few problems which cannot be handled in a sort of a normal situation. Yeah, this picture sort of would clarify things for you, right? So you have these two charge distributions, and you do integrate over one to get its potential, and then you get the potential at a point, at each point at the position of the second charge distribution. So that just to help you kind of imagine what's going on. We're going to take a look at an example of this just to illustrate the idea. And the result of the example actually is also quite interesting in terms of a general rule of thumb for electrostatic potentials. Okay, so we're going to say, this actually just comes from the book, but it's an interesting problem, so I will go through it in more details. So use Green's reciprocity theorem. It's actually relation, it's not typically called theorem. And an empty sphere with charge uniformly spread over its surface. Okay, so the problem is set up like this. You have a uniform sphere, empty inside, there's nothing inside, and charge only on the surface. And use this to prove the so-called mean value theorem. And what is that mean value theorem? The mean value theorem states that the average of phi of r over a spherical surface that encloses a charge-free volume is equal to the potential at the center of the sphere. Right, so we can basically write this down as if you calculate the potential at all the surface points, right? And then since we want to calculate the average value of the potential, you would have to divide it by the surface area, which you know is going to be 4 pi r squared. And that's the integral over the whole surface. That's the average value, right? We can call this as phi of r s, average value. So that means you calculated the value at all points on the space and divided by the surface area. And that is going to be equal to the potential at r equal to 0. That means at the origin, right? So that's what this mean value theorem means. And it's actually powerful, very useful. You can use that to in variety of situations. So let's look at the solution. So first thing, of course, for applying the Green's reciprocity relation is you need to identify two charge distributions, or at least a charge distribution and a potential. Right? And so for now, we have, that's our first step. Okay, so rho 1 of r in the reciprocity relation in this case is going to be rho of r, which is the charge distribution that's given to us, right? So the charge on the surface. And then if you calculate the potential R due to rho R, let's call that as phi 1 of R, right? So you need rho 1 R, rho 1 phi 1 and rho 2 phi 2. So that's good enough. This is fine. We need to now choose a reciprocal system. Right. Everybody okay with this so far? You guys have to turn your videos on so I can see you. Okay, very good. So everybody okay with that? What we need to do now is find rho 2 and R2. And so how do we do this? Rho 2 and phi 2 rather. How do we do this? Right, so that's the question. Okay. This is a little off. So let's see, rho 2 of R. This is actually not the charge on the surface. We're just going to say cal. Due to, so that's phi 1 of R. Some rho R, right? So we just keep them generic, right? So rho R and phi R are generic. Those are the ones that we want to determine, and rho 2 is specific to the problem, right? So that's how it's going to be. And now it's only on the spherical shell, total charge of Q. So we can calculate Q over 4 pi R squared. And you know, you can write this down in terms of a delta function, right? So a surface charge can be written down as a volume charge density. You know how that works, right? So that's how that's going to be. Phi 2 of R is going to be, you know, the charge density. So if you are within the sphere, so let's take a look at R less than or equal to R and R greater than or equal to R. You can divide the regions of phi into two different regions because you have a boundary, vacuum inside, vacuum outside, with a boundary with a charge in between, right, on that boundary. And so anybody remembers how this would work? Q over 4 pi epsilon 0. What is the potential inside of a sphere or a spherical shell where the charge is only on the surface? So think of the Earnshaw's theorem, right, which says that if you have a charge-free region, right, so the inside of the sphere, there cannot be a minima or a maxima of the potential. So the maxima or the minima is going to be only on the surface. And so that means it actually turns out that the gradient of the phi inside that whole sphere is 0 because there is no charge included in that. And that means it has to be constant. So provided you are within the sphere with little r less than capital R, you will have 1 over r. And as you go outside, it's going to drop down as 1 over little r. Everybody with me? Does that make sense? Just going to bring this closer. Okay. So with that, now we're going to try to use the reciprocity relation. Sorry, what's going on here? Okay, so now we have root 2 and phi 2, so we can say d cube r root 2 of r due to phi 1 of r is going to be equal to q over 4 pi r squared integral now just the surface integral phi of r, because delta of r is going to turn that volume integral essentially into a surface integral. And this you could see is just q times the average value of the potential on the surface, which is what we had it written down here. You could think of that as just phi average s, just a shorter notation. Everybody with me? All that we have done is we just said phi 1 is phi, right? The potential due to this whole configuration. And we just said, okay, do the integral with respect to root 2. So just first side of that equation. Okay. Now let's take a look at this second. So this is the left-hand side. Let's take a look at the right-hand side where you exchange the rule between row 2 and row 1. And there you would have d cube r prime, row 1 of r prime, phi 2 of r prime. And this integral is, we could take that row 1 is non-zero only outside the sphere, right? Because we essentially don't have access to the volume inside the sphere. And so what we want to do is restrict the integral only to r prime greater than r. And when we do that, we're just going to get, let me move this around a little bit. Phi 2 of r is something we already know. Outside, it just drops like 1 over r. So we will get 4 pi epsilon 0, 1 over r prime, right? And then we have rho of r prime, or d cube r prime. Now let's analyze what this is. This is essentially, if you do that integral, rho of r prime over r prime d cube r outside, right? When you're doing only the integral outside, that is essentially the potential at I'm going to do this, just do a slight modification here. Let's add one more step. So we do q over, we just keep the q as it is outside. And then we do this r prime over r, 1 over, I'm going to write this as 1 over 4 pi epsilon 0, rho of r prime, d cube r prime over r prime. Okay, can somebody help me identify what this is? You're integrating over r prime. So this is, if you wanted to add r, let's say this does look like a potential due to the charge density rho of r prime, right, which is maybe something outside. And we are trying to find potential at certain point r. What is that r? If that's what the expression looks like, what would be r in this case? Anybody has any thoughts? See, normally the distance parameter that goes in both the electric field expression or the magnetic field expression or even the potentials is 1 over the distance, right? R prime minus R when you're trying to find potential at point R due to, let's actually leave it as 1 and we put Q over 4 pi epsilon 0 here, or let's put rho of R prime d cube R prime. That's how we write this down, right? So compare that with the expression that you have. Okay, you are not off the hook yet. I am still looking for what's the specific value of R for which that expression is true.
Is it 0? Because
0, okay. Yeah, because R is missing, that's good. So that's
yes.
0, that means, yeah, very good. So that means what we have here is Q times phi evaluated at 0. So that's right-hand side. So equating now the left-hand side with right-hand side, what we have is Q times the average potential on the sphere is equal to Q times potential at position 0. That means phi 0 is equal to phi s in, for any charge-free volume for any charge-free volume confined by the surface S. Okay, so that means if there is a charge-free volume, I want to find the potential at certain point, what you have to do is imagine a surrounding sphere and calculate the potential at all those points and take the average value. Okay, that's how that works. That's how you get the, so it allows you sort of a numerically interpolation procedure. If you know field at certain points, you can find it inside at points that are not known to you because of this advantage offered by the theorem, and which we arrived at using Green's reciprocity relation. Okay, everybody with me? All right. Again, think about this, the finding these rho 1, rho 2 and phi 1, phi 2, that's crucial. Once you identify those, then it's going to be clear. So just to kind of help you, again, to illustrate this clearly, this is any charge outside. That's what I mean by generic, right? Any charge outside the sphere. And that's the corresponding potential due to that charge. Okay, so that's how we did it. So that means rho r, you don't have to specify. You don't really know rho r and phi r. You only know rho 2 and phi 2. And with the help of that, we use reciprocity relation to figure this out. So even though the problem did not have this reciprocity, we could use it to figure things out. And that's the idea there. There is another interesting problem in, before this one, that goes into the superposition principle for the electrostatics, which is, I believe, example 3.3 in the book. Yeah. So that I'm specifically asking you to read through that. So reading exercise for you. Okay, make sure you go through that. It's very nice looking problem. it allows you to figure out potential due to a surface charge which has uniform surface charge density, but a small cap is removed from it. And how would you go about doing, determining electric field in such configurations? So it's a illustration of superposition principle, if you will. So go ahead and take a look at that. That's a very clever trick that you probably haven't seen before. It's useful to do that. Another reading exercise that I want to add is the section 3.6. We have looked at the discussion of the total energy, total electrostatic energy, and why it's positive. But there are certain, there was this factor of half that I mentioned that you need to understand where that comes from. So that discussion is in that section. And there is also a very interesting application of the electrostatic total energy concept to ionization potentials of metal clusters. So some, kind of a modern problem where you can apply this idea. And I'm skipping the electric stress tensor right now. If we need to dig deeper, we will come to it in the next few lectures. So any thoughts, any questions so far about the basics of electrostatics? No thoughts, no questions, okay. Then I want to actually take a little digression here and point out things for your projects. They are all set up. So, okay, we're back. So we're going to now start a new chapter, which is electric multipoles, right? And we will just quickly set the stage for it and get on with this. So let me share my screen with you again. Okay. Right. So the idea behind multipole expansion is, let's first write down. And this is actually chapter 4. The chapter title actually is electric multipoles. So I was being more specific. It's more general. Okay. Okay, so what happens is most of the charge distributions that we encounter in our life are actually very small, right? Even if you look at biological samples, they're still very small, centimeter size. We are much larger. So when we observe the effects of these charge distributions that naturally exist, we are always very far away. We're trying to find electric fields potentials very far away from this charge potential. And so what we need to basically do is the potential that you can write down from the Coulomb idea has to be evaluated in a certain limit where the point R lies very, very far from R, capital R, and capital R is, let's say, the size, some size parameter of the charge distribution. right? And so it's this is called the far limit, far field limit. This idea even actually is useful in the field of optics. When you have some sources of light, the field profile looks very different when you are very close to the surface or very close to the source versus very far away from the force. So there are these near field limit and far field limit. And so to be able to do this far field limit, we basically just do a Taylor expansion, right, of essentially. And again, this is completely geometric. So let's now take a look at the steps in the electric multipole expansion. So what we are doing here is to find the far field limit expression for phi of r. That's our goal. Okay, so that's where the idea behind multipole expansion comes in. So let's now take a look at how it applies to specifically the case of electric multipole expansion. The idea, of course, works even in the magnetostatic case because it's completely geometric. You have this distance parameter, right, r minus r prime, and you have to expand this distance parameter within the limit that r prime is much, much smaller than r prime. So if that's the case, then we can take r is the large quantity. We can divide the numerator and denominator by r. So that allows us to do a Taylor expansion of this. It's essentially just Taylor expansion. And what we get is 1 over r minus, of course, the Taylor expansion in a 3D, right? So normally the Taylor expansion that you encounter is a single variable function. You're here now, you have a function of 6 variables, right? Because x, y, z, and x prime, y prime, z prime. So in r, okay, for r much, much larger than r prime, right? And so you get r prime dotted with gradient of 1 over r. The second term is positive. You get alternate positive and negative terms because of the negative sign in the denominator. If the sign in the denominator was positive, then all the terms would be of the same sign and positive. Now the second derivative is r prime dotted with gradient squared of applied to 1 over r. So everything is just applied to 1 over r, but you have the different kind of derivatives. So you have r prime dotted with gradient, r prime dotted with gradient squared, r prime dotted with, and so on. Okay, so that's the idea. And if you have questions about where do we get this expression from, go back to section 1.3.4 from the book. And there you will see this connection between Taylor expansions of functions of single variable versus multiple variables. Right? So that's the idea. And what we are geometrically, what we are doing is, I will just draw a little picture here. Let's take a size parameter. So the shaded area here is the charge distribution that you have, and the charge distribution are much smaller compared to our observation locations from there. And then let's take a look at, I'm gonna make this, that's the origin. The size parameter, roughly speaking, for this, I wonder why it's doing that. Just leave it there. That's R. That's the size parameter. And your integration variable is R prime here. And that's the charge density rho. And the observation point is really far away over here. Right? So you're trying to find phi of R at that point. That's basically the situation. So let's see what happens to the potential now if we use the Taylor expansion for 1 over R minus R prime. Right? So you just take phi of R, you know the expression 1 over 4 pi epsilon 0. Instead of now having just a single integral, we're going to have different components to it. So d cube R prime rho of R prime times 1 over R, then negative. Then you have d cube R prime rho of R prime Ri prime. Okay, where is that coming from? It's coming from the dot product, right? You can think of this as Ri prime dotted with, or just multiplied with, now dot is not necessary, Ri prime delta. Using the Einstein summation convention, you can think of this as Ri prime delta gradient I, right? And so you're going to have gradient I applied to 1 over R. And you could see the terms in the square brackets, they are actually just the functions of the source coordinate, the charge distribution over which you are summing over. And the rest of the terms are only dependent on the observation point coordinate, which is R. So this is going to be d cube R prime, rho of R prime. And now you are going to have, remember there are two dot products, right? So it's going to be Ri prime delta I, then Rj prime delta J. That's how that term is going to look like. I'm going to just highlight this so you sort of see that it's just a slightly different representation of that term using the Einstein summation convention. And the reason here, even when you square, first term, let's say, has 3, and the second term has 3. Total product gives you 3 times 3, 9 terms, and that's why I and J have to be carried over separately, right? So when we do that, we're going to have Ri prime, Rj prime, and then you have delta I, delta J applied to 1 over R, and then the rest of the terms. Everybody with me so far? And you obviously see this as an approximation, right? Because there are some terms that we're going to drop. We're going to say the terms that are ignored, over here are represented by the 3 dots. They are going to be negligible or small or whatever. So from this, now each one of the bracketed term, the square bracketed term, is going to be identified because it's now basically telling you something about the nature of the charge distribution in the sources, right? So that's all there is to it. So we define the moments, and those are called the electric moments, right? So let's write down the monopole moment. And you can see why it is electric, because it's connected with the electric charge. It's just basically the total charge, d cube R, rho of R. If you have a uniform volume charge density, if you have discrete charges, then you just have to sum over them, right? So we're going to simultaneously look at some discrete situations as well. Then we have electric dipole moment. And it turns out for any given realistic charge distribution, most of the materials that we encounter have, they have this sort of solid structure. So you have the positive and negative charges. Overall, it's neutral. I think Khaled initially had asked a question about most of the materials that we encounter are neutral. So do they generate their own electric fields? They do, right? Because the nature of the electric field is different, and that's important because for most of those materials, you will have the electric monopole moment to be zero. So if the electric monopole moment is zero, the contribution from the first term overall is going to go away. It does not create any electric potential. But then the second term becomes important. You may have charge distribution where both the electric monopole and dipole moment, both of them are zero. Then the quadrupole nature of the charge distribution becomes important. And these things are actually quite important. If you have taken the AMO physics class, how light interacts with matter depends a whole lot on these things. So if you have a material and you shine, say, put it inside electric field or shine laser on it, which you can think of laser as just the electric field associated with the light, then it turns out the first term, the monopole moment, does not contribute. It's the dipole moment that becomes important, and that dipole then interacts with the external electric field. There are situations where, according to quantum mechanical selection rules, again, you will learn that, or you may have learned that already in your quantum mechanics or the AMO class. The selection rules say that the dipole transitions are not allowed. So it's kind of equivalent to average dipole moment being zero. And then the quadrupole interaction becomes important. So the quadrupole moment of the charge distribution is very important, and that interacts with the magnetic fields of the laser light that you're applying. And so there are these variety of situations where these discussions are extremely important. So how do we define the dipole moment? It is essentially that second integral in the second term. And so it's going to be d cube r, rho of r, it's a vector. And so essentially it has three components, and you can split the integral into those three components and figure those out. Or if you have a discrete charge distribution, then you can calculate the dipole moment by essentially summing over the product Q alpha R alpha over all of the charges that you have. Let's take a look at now the quadrupole moment. So far, I think, unless you're doing something really exotic, you don't really have to go beyond the quadrupole moment, right? It's almost always, if these three, one of these three moments will be non-zero, and then that's all that you need to care about. So electric quadrupole moment, if you look at this term, it has two indices. So naturally, it is going to look like a tensor. Okay. So you can also see the monopole moment is a scalar. I will just actually write that here. This is a vector, and the quadrupole moment is going to turn out to be a tensor. Okay, because it has these two indices. And so let's write down then just the components of that tensors, components that are identified by the indices I and j. So you have this half t cube r, rho of r, ri, rj. Or if you have a discrete charge distribution, then it's just q alpha, r alpha I, r alpha j. Okay, that's how that is going to look like. Everybody with me so far? Any questions? Okay, so if we now separate out this sort of the geometrical charge distribution properties, then we can, in terms of the moments that we define, then we can write down the potential in a sort of a compact manner. It just has 1 over 4 pi epsilon 0 q over r. Then the dipole moment term is p dotted with r over r cubed. That's again just looking at the gradient. Let me do something here to point out where that one thing is coming from. You know how to evaluate this, and you know how to evaluate that part, for example. And so when you do that, that's where the R dependent terms are going to look like. So here it looks like P dotted with R over R cubed. So it still is like 1 over R squared behavior. And you can see that's going to drop down very quickly as you go farther away from the charge distribution. So first important contribution is the monopole contribution if Q is non-zero. If Q is 0, then you can, of course, ignore that, right? And then you go to the next term. The potential due to Qij, that one is tricky. And here in one of your homeworks, you are going to evaluate the double gradient applied to 1 over R. Looks like this. That's going to be something that you will do as a part of your homework to figure this out. I think you may already have done that. No, I think you will do it here. Okay, so that's kind of the situation. Everybody with me so far? So all of the important physics is already here, right? Then it's just applying these to a variety of different situations and investigating the field due to the electric dipole, electric quadrupole, and so on. So let's see if I can ask. Yes.
Could you please explain again about this last term? This is.
Yeah, so this term is, right, so let me highlight it. And let's also copy it. Sorry. This essentially comes from, okay, if you look at this, you have this del I, del J applied to R. So you have del I, del J applied to 1 over R. That's where it comes from. Okay. And this is something you can figure out, right? It's straightforward. You will see that this R squared term only survives when I and J are exactly the same. If they're not, then you don't have that term. You only have 3RIRJ over R to the 5. And overall, if you look at dimensionally, this goes like 1 over R cubed, right? So the electric, the contribution to the electric potential from the quadruple term is like 1 over R cubed. From the dipole term is like 1 over R squared. And from the monopole term is like 1 over R, right? Everybody with me? Okay, so that's how that idea works. Okay, and then let's now take a look at the dipole field quickly. We have plenty of time. So let's just now take a look at the dipole field. And one of the examples of a material that is neutral but would have the dipole moment is the water molecule, right? And so what you have is the O here, hydrogen here, and hydrogen here. So it has kind of a bent structure. The structure also becomes very important. And the book gives you in figure 4.2 the contours for the constant charge density. So you of course have more charge concentrated on the O part, right? And the hydrogen has overall less charge, even though H, O, and H, all three of them are neutral. The electron cloud is adjusted around, right? So the electron charge density is what causes the charges to be distributed. And the more electronic charge is going to be over here. So what you're going to have is, if you were to draw, and I'm going to try to make an attempt to draw the contours of the electric charge density as these dashed lines. And here, the density of these is going to be much larger. And as you get closer, these things kind of deform. So you're going to have something like this here, and then something like that. So as you go farther, the density of these contours is decreasing, and that's a measure of where the charge density has this largest amplitude. And then you will of course have things here. Yeah, okay. I don't think I can draw any more than that without wasting time and adding nothing really into the discussion, right? So the the overall dipole of this, and let me actually use the black color for this, overall dipole moment for this, because of how the electrons are drawn towards the O, so that's a negative charge. And you can think of this as maybe a vector addition of two dipoles, one along this bond, another one along that bond. But because these two vectors are going to add up, the vertical components cancel, so only the horizontal components are going to add up, and that is going to be your total overall dipole moment. Does that make sense? So the water is always going to behave like a polar molecule, meaning it has its own dipole moment. Overall, it's neutral, right? But it still has, because of these dipoles, it's now you have basically, when you have water, you have collection of dipoles. And so that's going to create interesting situations and nice electric kind of effects. Okay, so let's now take a look at how, if you have this dipole moment, how is the field going to look like? 1 over 4 pi epsilon 0 p dotted with r. So the observation point is important, r cubed, and this is true for far away from this, right? Okay, so p is non-zero when, so I'm just giving you a rule of thumb as to when dipole moments will be important, right? P is non-zero when the centers of the positive and negative charges of the given charge distribution do not coincide. Right. Let's take, for example, a simple situation where I have a positive charge here. I want to create a situation where the overall dipole moment will be 0, right? So let's take a positive charge Q, negative charge Q here, and at the same position, but just slightly off-centered, let's say, slightly above, I have another charge negative Q, and here another charge positive Q. Right. Overall, the total charge is 0, so you don't have to worry about that. And you have now two dipole moments. One, it always is starts, the vector starts from the negative charge and pointed towards the positive charge. So you have two vectors that are kind of overlapping with each other, even though they're just slightly off. The dipole moment for this is going to be 0, right? So the center of the positive charge and the negative charge coincide. That will be in the center of the line joining the two charges. Does that make sense? Everybody kind of with me there? Now it is sort of an artificial example. So let's say you have a little molecule there and another molecule there, and they are somehow, let's say, part of a crystal where the distance between them is fixed, right? So in that situation, both the centers for the positive charge and the negative charge are in center, and so they are overlapping. When they overlap, you're not going to get any dipole moment. Okay, so let me just put this in a box. Okay, so that's just sort of an example situation. Now let's take a look at, we don't care about where this sort of the dipole arises. It just comes naturally from the charge distribution, but we should be able to understand the properties of this, right? Okay, so when we say P is non-zero, this kind of materials have permanent dipole moment. And in this case, it's permanent electric dipole moment. Magnets, which you're familiar with, magnets have a permanent magnetic dipole moment. That's why they have this magnetic field that they always create, right? So that's that connection between them. So what we call polar molecules are essentially electrates, right? So you can call H2O essentially as like on, similar to the term magnet. These are electrates, right? They can create their own electric field around them, even though they are neutral electrically, because of this separation between the negative and the positive charges in the material. Okay. Now you can also have induced dipole moment. And that's when you apply external field electric field, the charges separate, the positive and negative. Why would they separate? Because the force on the two opposite charges is opposite. So and whenever you have positive and negative charges separate, that's going to lead to a dipole moment, right? Okay. And that's how that idea works, right? And you can kind of take a look at the definition of the electric dipole moment, and you will see that the charge separation is what leads to. In fact, this is a much better or simpler expression to use to think about that. Why you need charge separation for, because of that R alpha term. It depends on the position. Another weird thing about dipole moment is it is actually dependent on the choice of the coordinate system. Right, so that's just something a little bit weird. In general, right? So let's actually clarify that a little bit. Okay, if Q is 0, right? So only in that case, this is actually very useful. If Q is 0, then P is independent of the choice of origin. Okay, so let's kind of verify that. Let's say P prime is a new dipole moment that is obtained by shifting the position where, because we change the origin, each one of the coordinates R is obtained by a new coordinate system corresponding to R prime plus the shift, right? So let's actually draw a little picture. So that's O. I'm just going to draw a two-dimensional thing, and then another. Let's use the dashed line for the new location of the origin. And so this is O prime. And the vector that relates the two is this vector D. Okay. And so let's now calculate. So if R and R prime are related by this vector, and so here's some point that we are trying to find the position of. This is vector R, and that is vector R prime. So R prime plus D gives you R. Okay, so that's how that works. R vector is actually here. Maybe I should just label it there. R vector is here, R prime vector is there, and D vector is there. So you can see the vectorial relation. Now let's prove that the dipole moment would not change just because you moved your coordinate system, right? That would
The
be
point is
terrible because
P.
what's that?
The point is P here.
No, point is not P. P is the dipole moment, right? So some observation point here is what we are trying to. Okay, I'm going to move the label for the coordinate system O prime. Yeah, it's R is just the observation point, right? So let's calculate the P prime is going to be in the new coordinate system, d cube R prime, rho of R prime times R prime. Everybody with me so far? That's the definition of the dipole moment. But we wrote it in the new coordinate system. Now let's transform it, right? So first thing is the expression for rho R is going to be the same as expression for rho R prime. That's not going to change. D cube R and D cube R prime, they're going to look the same. So it's like a dummy variable, so nothing changes. So only thing that changes is this quantity here. And so let's substitute that. So I'm going to write this as D cube R, rho of R, right? No R prime now. And R prime is replaced with R minus D. And so that gives us the total dipole moment that we had to begin with, minus, now D is a constant vector, so you can take it outside of the integral side, integral over the charge distribution. That gives you the total charge Q times D, right? So only if Q is equal to 0, P is independent of the coordinate system. If Q is not 0, then dipole moment changes. Okay, everybody with me? So we just proved that for you. And this is crucial. This is one example. It is similar actually to a classical mechanical situation where the angular momentum of a mechanical system depends on the choice of coordinate system, right? So the actual value does. And even in general, even the dipole moment does. But if Q is 0, then you don't need to worry about that. Then P prime is same as P. Okay, everybody with me? Any questions? So that is now the dipole potential. Let's calculate quickly the electric field, and then I will show you the plot of how the electric field looks like, because you know how the electric field looks like from a spherically symmetric uniform charge distribution or a point charge, right? So those have essentially the same symmetry. So you have to take the gradient of phi with respect to R, and when you do that, again, it is a little bit involved calculation. So I'm going to have that as a assignment for you. That's how it looks like. It's quite complicated expression because it involves several dot products and then so on. So, but each one of them is a vector. So R hat dotted with P is just the component of P along the radial direction. And then somehow the coefficient of 3 appears there. And then you take that quantity, subtract P from it, and then it goes like 1 over R cubed, right? So this is how it looks. It actually looks very complex in this, but in the spherical, in the polar coordinates, the 2D polar coordinates, it actually is very simple. So let's write it down in the polar coordinates. And let's take the dipole moment to be along the z direction. So you kind of have the dipole moment over here in the z direction, and the c coordinate you can write down in terms of the polar coordinate as r cosine theta minus theta hat sine theta. Okay, so that's just connecting the two coordinates with each other. Then the electric field as a function of r and theta looks like P over 4 pi epsilon 0 r cubed. So that's just the dipole moment and the distance dependence. Very simple, but there is now some angular dependence that comes in. if you look at, for example, a electric field due to a point charge or a spherical symmetric charge distribution, there is no theta or phi dependence, theta and phi being the angular coordinates in the 3D coordinate system. There's only the r dependence. But for the dipoles, that's not the case, because the source, which is the dipole itself, is a vector. Now the dot product between the dipole moment and the r vector of the point at which you're trying to find the field at, the dot product becomes important, right? So you have these two components. So it has a radial as well as a theta component. And the field lines, actually, I'm just going to make an attempt at drawing them with, let's say, a different color. They look like this. If you're close by, again, you can see this goes like 1/r cubed. So the closer you are, the higher, the denser the field is, and the farther away, it looks like this. And this is very similar to the magnetic field of a permanent magnet, right? Which is, like I said, it's a dipole is essentially an electroid, right? So you get this field here, these lines, and the arrows like this. So if you bring a little test charge and place it in there, it's actually going to go travel along that curve, because that does not cause any energy. And as you go farther away from it, the density of these lines is much larger near the poles, and as you go farther away from the dipole, then you don't have much of the. There's another line, then another line. And in the next class, after the spring break, we will actually try to plot this. So I didn't do a good job, but you can actually get Mathematica to plot this. And so we will try to do that next time. Okay. And let me add the arrows. Right. So that's how that works. Okay. And then another cool thing that you can do here, it's trying to connect with mechanics. If you look at two symmetrically placed dots here, right, and think of the dipole as along the z direction, and this pattern that you see, it's independent of the rotation. So you can actually rotate it, and it will create similar structures. So these even if you rotate, if you look at slightly angled direction, the pattern will look exactly symmetric. So it's sort of like a donut structure, then, if you will, surrounding the dipole, right? And so these 2 points that I have labeled in blue, that will essentially form a circle as you rotate this pattern around the dipole itself. And so you can actually have a stable orbit. The electric field is the same at all of those points on that line, and you can have stable orbits of a test charge. It will just sit there and it will go around. And so you can have variety of interesting, even mechanical situations that lead to the dipole field properties. Okay, very good. Any questions? Again, we're not completely done with the discussion of dipoles. We will work on that in the next time when we are back. There are quite a few approximations that we have to make in making this more general, but we will do that. And then we will study the quadruple field as well. Thoughts, questions?